Hi everyone, this is a quick set of notes on magnetism. I'm going to put myself over here. Maybe that will, nope. I think I have to move myself down here. It's okay. All right, magnetism and electrical forces. So first we are going to go over magnetic forces. So here we go. So just to begin with, what are some basic things about magnets? Okay, things that we all know is that it's going to be made out of metal and it will attract other things that are also magnetic that are also made out of metal. You can see what all of this includes. It includes iron, nickel, cobalt, and some mixes of metals. We call those alloys. We'll get to that when we get into chemistry. And our most famous for our area is steel. That's why we're called Steel City, because we created some of that steel. Okay, you have two major types of magnets, and that's going to be permanent and temporary magnets. So as you can see with our definition here, the permanent magnets, they create and they keep their magnetic fields without any outside interference. They are also called ferromagnets, and the main example of a ferromagnet is iron. If you eventually see the periodic table, iron's original name was ferrium, I think, or something like that. And that's why on the periodic table, iron's little symbol is Fe. So that's why they call it ferromagnet, is because it was all originated with iron. Temporary magnets, you can see there, they are going to be metals that don't have their own, for sure, magnetism, but can become magnetized when you have electricity or another magnet around it. Once that source is removed, then they stop being a magnet as well. As you can see in the top right corner here, magnets can also be weak or strong. So you have like a weak magnet, like the ones on your refrigerator, and then you have something called an MRI. MRI is magnetic something imaging, okay? And that magnetic part for an MRI is actually like 200 times stronger than your refrigerator magnet. So, yeah, got to be careful around those things. Okay, magnetic poles. You can, again, no surprise to you, there's a north and a south pole to magnets, and you can see here that if it's the same pole, like south and north, that they are going to actually repel each other instead of attract each other. Okay, you can also see there that the force that the magnet has will be stronger at the end of the pole instead of at the middle. And I will show you why here in a second. So magnetic field. A magnetic field is, as you are, again, shockingly, invisible, that surrounds the magnet. The magnetic fields apply force to other magnets even though they are not in contact. Remember, we call this a force, or a field force. When we did Newton's laws back in the day, gravity is another one where it doesn't actually have to be in contact to actually pull. Same thing with magnets. And you can see here the shape and the strength of the field can be represented by iron filings. So you see where the iron filings are very close together. That means it's stronger than it is weaker here in the middle. Another thing is, I can't really remember. Oh, there it is. Okay. The magnetic field around a bar magnet, the arrows show the field lines and the direction that it moves. So you can see it moves out from the north and wraps around and goes into the south. Okay. So, and you can see here, the stronger the magnetic field, the more lines you'll have. But that is why, if I come back, well, I'm going to move this thing out of the way because it's in the way. When you come back here, south and north, because the field is exiting the north and entering the south, that's why you have south and south repelling and north repelling, is because they are going the same direction of that field force. So there you go. Compasses, This is also important. The needle of the compass is basically a small magnet. It has a north side and a south side. And it's not that the north arrow actually is attracted to the north end as much as it's just lining up with those fields. So you can see it here, it lines up with this field, and if you move here, it'll line up even pointing towards the south. And so that's why a compass works the way it does. Magnetic domains. The magnetic domain is when all of the little atoms in that object will actually line up together in order to make it magnetic. So you have non-magnetic materials like this comb here. You see how all of the north and south ends of the atoms are all pointed in random ways. Here you have an iron nail. Here, I'm going to move myself here. An iron nail has these little pockets where they are lined up, but those pockets don't match up with other pockets. So an iron nail by itself will not be able to be a magnet, or at least a strong magnet, okay? Now you actually have a bar magnet, and you can see here that everything lines up nice and pretty. Now with this iron, because we did say that iron is a magnet, what happens is that iron nail will be like around electricity or another magnet, and what happens, oh, I have it right here, okay? So what happens is when this iron nail is lined up appropriately with, or is near a magnet, what's going to happen is that all of those little pockets line up and it becomes a temporary magnet. So here's your temporary magnet again. I just got a screenshot of it and put it right here. So they enter another magnetic field, so like we see here, or around an electrical current, which we are about to do, and they will all line up. And so as soon as that magnet is taken away, they all kind of go back to the way they were. All right, electric forces. I'll move myself again. Electric charges, these are tiny particles. We haven't gotten to this yet. This is more into chemistry, so you'll see that really science is all kind of connected and everything. So there are positive and negative charges. They're very similar to magnets. It's almost identical. So as you can see in the picture below here, like charges attract each other, and similar or like the same repel. So it's like the thing you've always heard, opposites attract. So that's what we're seeing here. Also, similarity of forces at a distance. Okay, so they can either push you away or pull you. That's what this sentence means. So it depends on what that charge is. It can either push away or pull, and it depends on what kind of charge you have as well. Electrical field lines, again, it's the exact same thing as magnets. They're just not made out of metal. And so you'll have the positive end flowing into the negative end, and so you have that, and you can see why these are all repelling is because they are trying to flow out, so they don't want to be around each other. So again, it's very, very similar to magnets. Electrical field strength, so it depends on two things, distance and total charge. So you have, oh, I forgot to get my example here. That's okay, we'll do it later. Never mind, we're going to do it right now. So we have this lovely thing, I don't know why, but on the A cap, they love to call these, like, instead of a glass stirring stick, they call it glass rod, but you know, whatever it is what it is. So what I have here is, it's glass, you can see, it is definitely glass. I have this cloth, and then I have a piece of plastic here. So what, and this is nothing that you don't already know, like when you, are rubbing your feet on the floor in winter, and then you go and touch your brother or your sister or something like that, you shock them. It's the same thing. So if you rub this cloth against a glass rod, what happens is that there's an attractive force. So you can see it, like if it's away, it's nice and flat, hanging low, but then you move it together, and all of a sudden that plastic is moving towards your glass stir stick. Now, that is because with this cloth that I rubbed all over this glass, I was able to steals some of the electrons or the negative charges from that, and then the positive charges off of this, they were able to attract to each other. Another example is lightning buildup. So even though there's a lot of distance here, there's even more of a difference in the positives and the negatives. So much so that it's willing to cross over air, which doesn't conduct electricity very easily, but it's so strong that it's willing to conduct electricity at that point. So there's so much positives, so many negatives, and it's really these lower clouds right here that build up in these negatives because the wind is moving and causing all that friction to happen. And then you have the negative in the sky coming to the positive on the ground, and all of a sudden it gets too much and it wants to be nice and neutral. Touchscreens also use static electricity, so what you can see here is that it feels the change in electricity from your finger. You do have, all humans run on a little bit of electricity, so when it senses that, it will sense that touch. Then you have that silk cloth with the glass and all that kind of stuff. Static electricity, most objects are neutral and they want to be neutral. You can see here you have this picture of the sweater. It has all these positives and negatives, and this balloon has positives and negatives. I'm going to move myself again up here. Okay, so after you rub a balloon on your sweater, and we'll learn this eventually, but what really happens is that the negative charges are on the outside of all of the particles that everything is made out of, and the positives are on the inside, so it's easier to take the negatives away. So that's what you're seeing here. When you rub a balloon on a sweater or your hair or whatever, it steals all of those negatives because it's easy to grab those off. And then when you bring it away, or like if you have a balloon and you bring it away, the hair or sweater or whatever is attracted to it, so you'll see your hair moving along with it. Okay, this is, I think, our last little bit, conductors and insulators. So there are conductors which allow electricity to flow easily, and then insulators that don't. So conductors, they are really loosey-goosey with their electrons or their negative charges, and so they don't hold them very tightly. This is going to be anything that's made out of metal. It says water here, but it's really like salty water or like tap water, not like pure water, because pure water doesn't like to have electricity, but like regular tap water or water that is in the ocean or in the lakes or rivers, they have like other impurities added into it, so they would be good conductors. Insulators, things that block the flow of electricity. Basically anything rubber. This is why your charging cords are wrapped in rubber, is because it doesn't want you to shock yourself when you plug your computer into a wall that has 120 volts of electricity, which can possibly stop your heart. So you don't want to do that. And then you can see all of the other examples there. All right, I think that's all I had. Is it? Yes, it is. All right, y'all. Hope this helps.